background. But he's given a few of us, probably not very many here, we have seen this presentation before, but maybe just 2 or 3 of us have, and it's excellent. So some of it's, again, most of it's going to be, feel like it's kind of over our heads, but you guys are all going to understand the gist of what's being presented. So you're going to be fascinated by what he's presenting, and I'm so thankful to Fred for all the time he's put in to this presentation tonight and putting together special notes for us so we can take notes and then discuss afterwards. So we're going to use the same format tonight of presenting, and then we will, the women will go into the conference room and we'll talk and discuss the questions, and Fred will stay here with the men. And we'll have a little bit of time to just discuss what he's presented. So thank you so much, Fred. Introduce yourself, please.
Thank you, Brenda. Yeah, this is all going to be over your heads because it's all about space and cosmos. Yes, of course it's over your head. But yeah, I'm Fred Poland. By training and profession, I'm a geologist. I work for a software company. We develop the software that geoscientists use to look for oil and gas. So I've always been interested in apologetics, but particularly in bringing both science and faith together. A lot of people aren't comfortable with even giving Christianity a thought because, oh, they learned in science class that, oh, you know, we can explain everything by natural causes. Well, not so fast, not necessarily so. So I've spent a lot of time, probably the last 25 years, just being involved in Christian scientific apologetics. And I was asked about a year ago by Ike Shepherdson to prepare a talk on fine-tuning. That's one of the arguments for God. You know, there's 5, 6, 7 different arguments for God. One is the cosmological argument is like, where did the universe come from? One is the design argument, it's called the teleological argument, that means fit for design. That's what I'm going to be talking about. Then one is the moral argument for God, the origin of life, and the various other ones. So for the chapter that he was covering in a William Lane Craig book, he wanted me to talk about the fit for design and the design argument, the teleological argument. So I put together a presentation. I actually leaned heavily upon some books. Some of you may be familiar with a ministry called Reasons to Believe by Hugh Ross out of California. He has a ministry that's been out there over 30 years, and I've probably been around it for 25. And the mission is to reconcile science and faith, to lower the barriers to entry to people who are seeker-friendly, but maybe have a scientific bent and need a little bit of help getting over that hump. And that's kind of what I'm talking about here. So in talking about the fine-tuning argument, what I'm going to be talking about is going from the very, 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 very largest scales of the universe. You may not even be familiar with them. I wasn't familiar with them until I started doing the research for this. And we're going to cascade down smaller and smaller scales and look at each of those scales and look at the fine-tuning necessary at each of those scales of the cosmos in order for us to be here tonight talking about this. And it's just absolutely amazing. Now, if you stop at the scale of kind of the Earth's surface, I don't go on down to the microbes and to the atoms and to the protons and to the quarks and to the strings and all that. But that's a whole nother universe going on down that direction. So with that, can everybody hear me okay? Now, I would encourage people to move forward, but you know, if you can't bring Muhammad to the mountain, you have to bring the mountain to Muhammad. So I'm going to move this a little closer. If I can. And that's a metaphor I can use because I actually work for a Muslim company. So it's probably too much. Well, I should say I work for a company out of Islamabad. Well, a year and a half ago, I was manning a booth up in Boulder with the Reasons to Believe group. Again, you have the Boulder Beef Festival, you get all kinds of people there, all kind of booths there, all kind of food there. And one of the booths that was down from Myers was the atheist booth. So I went down to talk to the people there, talked to this lady there, and I asked her, you know, I can understand why people might be agnostic, but I can't understand how you can be an atheist. And I said, why are you an atheist? Why don't you believe in God? And she said, there's no evidence. And I said, wait a minute, the evidence is all around you. You know, where did the universe come from? What about all the fine tuning of the natural properties of nature? What about the origin of life and all these things? And she said, well, science just hasn't discovered that yet. So I said, oh, you actually are a person of faith after all, because you don't know that you will ever discover those things. So anyway, what it kind of led me to think about, we think we're so sophisticated. You know, we have the internet, we have AI, machine learning, all this stuff out there. We think we were so smart. But the people back in the times when they wrote these verses in the Bible were actually quite sophisticated in their own right. They were not distracted by all the things we're distracted. I have a hard time working sometimes because I've got YouTube right there to go look at something interesting, so it distracts me. But back then, they had a much simpler life. They were much closer to nature. And at night, they had no light pollution. So when they looked at the heavens, they could see the Milky Way, they could see the stars. And so they said, you know, or speak of the earth and it will teach you. They grew things, they mined things out of the earth. They were very, very dependent on the earth for their sustenance. And in light, they can see the heavens. The heavens declare the glory of God. The skies proclaim the works of his hands. That's in Psalms. That's what, 1,500 years old. For since the creation of the world, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood from what has been made, people without excuse. Really an insight. So what we're going to do, if the internet will permit me, and I will just make an excuse ahead of time that we have a little bit of technical difficulties, we're going to start by looking at the powers of 10. We're going to start with something that we're all familiar with. It's going to start in Venice. And then by the powers of 10, we're going to start looking at larger and larger and larger scales. So it gives you some context of what I'm going to talk about. And then I'm going to take you step by step from the largest scales and talk about the fine-tuning properties of each of those scales. It has to be just such so that life can be possible here on Earth. So I hope you just strap on. Don't worry about understanding all this. I think you'll get the context of it as we go and just enjoy it.
Since the universe is a big place, we could easily get lost. So we'll need signposts to give us a sense of scale. The Amberbatch rim is 1 meter wide. The crowd is 10 times wider, 10 meters across, larger by 1 power of 10. Now, with every step, every ring, we travel 10 times farther from Venice, and our view of the universe is 10 times wider. The 100-meter ring surrounds St. Mark's, and 1,000 meters, 1 kilometer, the city center. As our speed increases, 4 steps, 4 powers of 10, reveal all the islands of Venice, the Adriatic Sea, and the mainland of northern Italy. Six steps taking Europe from central Germany across Italy to the Balkans. But soon we can see the entire planet, our home in space. Eight steps on our outward journey, 8 powers of 10, and we pass the farthest reaches of human travel, the moon. If we visualize the paths that the 9 planets take in their orbits around the sun, at 13 steps from St. Mark's Square, the entire solar system comes into view. 15 steps, 15 powers of 10, we can see that our sun is just another star. From here on, our voyage will be measured in light years, the distance light travels in an entire year. Only now do we fly past our nearest neighbor stars, almost 5 light years away. The same journey at the speed of today's spacecraft would last 100,000 years. From perpetual night, our voyage takes us up and out of our sun's neighborhood, near the edge of a great pinwheel of stars. The Milky Way is actually a spiral galaxy, and our own sun is just one of 100 billion stars in it. At this immense scale, 23 powers of 10, each shining light we see is not a star, but an entire galaxy, composed of countless stars. Astronomers have discovered that the galaxies are flying away from one another. The universe is expanding. Our own galaxy and all the others form clusters and superclusters of stupendous size, hundreds of millions of light years across. Here, about 15 billion light years from Venice, we approach the outer limits of the visible universe. What lies beyond this cosmic horizon, we cannot see and do not know.
I think most of you are probably familiar with galaxies if you're a Star Trek fan or Star Wars fan, you know, in a galaxy far, far away. So it's gotten into the common lexicon out there. But not a lot of people understand that these galaxies are actually parts of larger structures called clusters of galaxies that are bound gravitationally together, and even superclusters that bound the clusters together in the largest structures that we can see in the universe. So I've got another video here that gives you a little bit of an idea of what they call the cosmic web. The cosmic web is made up of these filaments, of these superclusters of galaxies wrapped together, held together by gravitational and dark matter. So just to give you a context of what the cosmic web is about, we'll take a look at this video. We're buffering right now, so replay you should do. It's almost like a sponge.
Does it have words? I mean,
No.
sound?
No, it's just showing the tendrils you're seeing there are not stars, but they're the galaxies. Each of those little lights is a galaxy. So that's what the cosmic web looks like, the largest scales that we can detect.
So it looks like the galaxies are connected to each other through this.
They are. They're the clusters and these filaments that we're talking about in just a moment. I just want to give you again what these things look like at the largest scales.
Okay. Are the colors true?
The colors, the yellow, probably not true colors. Just they're done that way so we can see them. May not even be in visible light. But the yellow and the white are regular matter. The purple color in there is the halo of dark matter. And there's actually, we only see 5% of what's seen in the universe. 95% of the universe is invisible to us. made up of either dark matter, but you don't know what it is, that's why we call it dark, or dark energy, and that's the repulsive energy that's forcing the universe to expand. We don't know what that is yet either, but that makes up 95%. So really, we only can see 5% of actually what's out there. Now, we live in a supercluster, we call it a Laniakea supercluster. That means measurable heaven in Hawaii. And because of the structure of the Laniakea supercluster is special compared to these other superclusters. Most of the clusters out there are almost like foam, like bubbles, like a sponge I was showing you. But the Laniakea supercluster has a very unique shape, and our galaxies occupy a very special place within the Laniakea supercluster. Almost like a horsetail type construction. And you see, we are occupied over here in one of these little outposts on a little timberland. And this is very important because it places us away from the high concentration of other superclusters, because they would have very strong gravitational forces and also the concentration of radiation. So it's gravitation and radiation, the highest structures that are most deadly to us. We want to be as far away from high concentration of galaxies, and we'll get down to other scales, to be separated from the disturbing perturbations that gravitational forces would force upon us, and also the radiation caused by the galaxies, the supermassive black holes within the galaxies. So again, location, just like in real estate, the best location is the place you want to live. And same thing within the galaxy itself. So let's now go down to the next scale. Now, within the Laniakea supercluster are clusters of galaxies, and we are within what's called the Virgo cluster. And again, you can see it's kind of drawn out, and we are occupying this space up here in the local group. Again, we're kind of away from this Virgo, the center of the Virgo supercluster, or some of the side superclusters, again, being away from the gravitational perturbations and the extreme radiation that would be deadly to life. Now, within the Virgo supercluster, our little area is called a local group. And this local group is where our Milky Way is. And in our local group is the Andromeda Galaxy. The Andromeda Galaxy is about 2 million light years away. And it's also a spiral galaxy of approximately the same size as the Milky Way. And it's heading straight for us. But fortunately, it's far enough away that its gravitational influences are minimal. So it's not going to tear up the structure. Both the Milky Way and the Andromeda Galaxy are beautiful spiral galaxies that have not been torn apart by other galaxies influence. So it's far enough away, even though it's heading for us. Don't worry, it's not going to get here for a billion years or so. So not too worried. But again, around the Milky Way, you'll see a bunch of other. So there's the Andromeda Galaxy right there. You'll see other little galaxies. These are called dwarf galaxies. And there's a couple of other ones in here called Magellanic Clouds. These are galaxies that are gravitationally bound to our local group. And it's fortunate we have them, particularly the large and small Magellanic Clouds, which are only viewable from the southern hemisphere. That's called Magellan. saw and reported. They help maintain the spiral structure. Now, it's very important that the Milky Way have a certain structure, and we'll get into that as we go down the next scale. But the Magellanic Clouds help us maintain that spiral structure. Also, the Magellanic Clouds are feeding gas into the Milky Way to provide star formation. You need that gas. Gas is mainly made up of hydrogen, some helium, some dust, but that hydrogen mainly is the fuel that forms stars when they collect gravitation. So in the Milky Way, we're still making new stars. We're not such an old galaxy as we run out of fuel. And the Magellanic Clouds help continuously feed us gases to create more and more stars within our Milky Way. So let's take down the next scale. Our Milky Way galaxy. We're pretty familiar with that. I think everybody's seen the galaxy. Back in the 60s and 70s, there was a Ford galaxy. So obviously it was in the popular lexicon at the time. But it's a beautiful spiral galaxy with a central bar here. Now, this means that it's not been disturbed because it has beautiful symmetrical structure. It's not been disturbed for billions of years, which is a good thing. Because again, it has to have the right age. It has to have the right composition of elements heavier than hydrogen, helium, and lithium. In other words, this has to be old enough that it's had enough star formation to have nucleosynthesis. All the elements in the periodic table down, well, basically all the elements of the periodic table past maybe lithium, because hydrogen has 1 proton, helium has 2, lithium has 3. Form from what's called nucleogenesis. When stars, they get old, they burn up their fuel, and then they collapse under heavy gravitational forces, and then they start to burn the next element. Like when the sun runs out of fuel, it'll collapse down and start building helium. And when the helium generates other elements like carbon, when that's used up, the star is big enough, it will collapse more and start burning the carbon and form heavier things, all the way down to iron. So the Milky Way galaxy is of the right age, right composition, to have the stars of the right age and composition to generate the elements that we need to support our bodies in modern life. And then when these stars explode in massive supernova, everybody's heard about supernovas out there. It scatters all this stuff into space to then to collect into other stars and solar systems. And we'll get to that very, very shortly. Do you have any questions, or if I'm going too fast? Yes.
Where is the Earth in that?
We will.
I mean, where is our solar system?
Okay, we are, well, you're a good straight person. We're between the Perseus and the Sagittarius arm here. So right here, this is called the local arm. This is where we reside. Thank you for that question. So here's the Milky Way. Here's the Sagittarius arm. There's the Perseus arm, and then there's a small little arm called the Orion arm. We're kind of right at the edge of it. Again, location, location, location. If we were to the Sagittarius or Perseus arms, we'd be too close to other stars, black holes, radiation, and again, gravity. We're out here kind of in the boonies, but not so far in the boonies that we aren't close enough to the core of the galaxy that we are fed the higher weighted elements beyond lithium, hydrogen, helium, things like that. So that we are close enough that we have these heavier elements that we need to make a rocky planet that we can mine and have more. And in our bodies, we need iron, we need potassium, we need calcium, all these good things made by the stars. We're just in the right place. The other interesting thing about the place we are within the galaxy is because these galaxies actually rotate. These arms do rotate, but the stars do not rotate with the arm. It's almost like a wave. When you send a wave through water, you see that if you have a bobber in there, you'll see the wave go out, but the bobber kind of stays in the same place. It's a little bit the same way. So as the universe, as the galaxy spins, we are at what's called a co-rotation place. That means that this position right here will not cross one of these spiral arms very often. If we cross one of these, the Perseus or the Sagittarius spiral arm, again, we would be subject to gravitational and radiation effects. So this little video down here kind of shows you that as this spins, these arms are constantly renewed by other stars that actually flow into it, almost like a wave. So you see, if you just follow a star, it actually passes through the arm, and these arms don't pull the stars along. These are almost like waves within the spiral structure of the Milky Way. And we're fortunate because we stay out here to kind of rotate, again, we kind of rotate with the rotation like this. So that we only rarely cross those spiral arms, and probably hadn't happened in the last billion years. The other thing is, if you turn the Milky Way galaxy on the side, it's a spiral, it's a disk. And in the middle of the Milky Way galaxy is a supermassive black hole. And about 2 or 3 years ago, those who are interested might have read that they actually have an image of that supermassive black hole in the center of our galaxy, which is a really cool thing to think about, that they could actually put together an image of it. Well, that supermassive black hole holds together the whole Milky Way galaxy, but it also emits tremendous amounts of radiation. Now, if you're in a disk, there's a Milky Way. If you're in a disk and a supermassive black hole is in the middle, this is fully rotating, and you're in a star, you don't want to bobble up and down as this thing rotates. You do not want to bobble up and down above or below the galactic plane, because then you would be no longer shielded by all the stars within the spiral arms. If you bobbled up here, you would be in direct alignment with that supermassive black hole, and again would be fried. So that's another unique thing about our position within the Milky Way. Most stars do bobble up and down as they rotate. But again, in our position, we stay pretty much within the galactic plane as this thing rotates. So we're always shielded from that supermassive black hole radiation. Yes.
You talked about the universe is expanding because of dark matter,
Dark energy.
dark energy. So there's a difference between matter and energy.
Yes.
Okay, so the dark energy is pushing the universe out. Our black holes are different than black energy.
Yeah, black holes are just, if you collect enough matter and it collapses under gravity, and it sucks in more and more matter, and collapses more and more, gets more densely concentrated, its gravitational field goes up. And it gets to the point that the gravitation is so strong that even light cannot escape it. So that's the definition of a black hole. It's called black because nothing escapes. It's whole because it's a black hole, I guess. But dark energy, the only reason we know that dark energy is out there is because of its gravitational effects. It does not interact with radiation. We can't see it, we can't detect it. We can detect it because the galaxies out there are actually rotating faster than they should, based upon the visible matter out there. So that's how it's kind of a deduction of saying, wait a minute, it's spinning too fast, according to what we calculate as the amount of mass that we can see. Therefore, there must be some invisible or black matter out there.
So black matter black energy, black.
Now that's matter. That's
Okay.
dark energy. Dark energy is think of it kind of like antimatter. It's the repulsive force. So after the Big Bang happened, there was a period called inflation, where everything inflated tremendously, much faster than the speed of light, and spread everything out. And then it started slowing down and expanding. We thought that at some point it would go up and expand to a certain point, stop, and then collapse back on itself and back. Being piled up and goes away from you, those wavelengths of sound are being spread out. It's the low pitch. Same thing happens with light. You know, as light recedes, as the object making light recedes, it spreads out that wavelength. But so so from the called redshift, we know that the universe is expanding. But then they discovered back in the 90s that not only is it expanding, it's speeding up. And they don't know why. That's why they call it dark energy. And that's one area of tremendous amount of research right now, trying to figure out what it is.
I don't know if it's significant that one, they're different things, but one is. The dark energy is pushing out, and then the black hole is.
Dark matter. Yeah, it's
No.
solid.
So there's one force that's pushing out, and then another force that is.
Pulling it in.
Pulling in. I don't know if that's significant.
You know, you're on something there, because that was exactly what people were wondering, was that as the universe is expanding, was it slowing down because of the gravitational of visible energy and dark visible matter, dark matter, and then at one point it would stop and then collapse on itself. And what they found out, it went out, but then it started to speed up. Well, what's making it speed up? We don't really know. But everything is there for a purpose. If it wasn't so, then it would affect everything down the scales. Everything's finely tuned all the way together. We're not even talking about the finely tuned forces of nature. That's what we're talking. I'm just talking about the finely tuned of the cosmos at all these different scales has to be just such. And if it weren't just such, we wouldn't be sitting here having these conversations. So these are great questions. Thank you. Okay, the sun, our old friend, the sun. You've heard that, oh, the sun is just an ordinary star, and you heard that. It's anything but an ordinary star. It's what we call a second or third generation star. Remember I said within the Milky Way, you have star formations, and they collapse and burn up their fuel. They synthesize more and more heavy elements, and then at some portion they explode and spread all the stuff out. Well, our sun is made up of that stardust, if you will, of second and third generation suns out there that collapse and explode and spread all the material out in space, and then it collapses again. So the sun really has a lot of matter in it, or elements in it, other than just hydrogen, helium. It contains all of the elements that are within the solar system. Now, when it formed in just such a way that it made the rocky planets near to the side. That's because rocky planets had an atmosphere at one time, but the sun blew off all that atmosphere. And then the farther away, you've got the gas giants, and those are the big planets because it's cold away from us. So, but the main thing about our sun, it's been very, very stable for millions of years. It has very low flaring activity. You've heard of aurora borealis, things like that, northern lights. Well, that's caused by the sun flares, which shoots out high energy particles into space. And if it's pointing at us and it fires off at us, it intersects the Earth. But fortunately, the Earth has a magnetic field. We'll talk about that. And it's kind of like a bar magnet. And it deflects all that solar wind up to the northern and the southern poles. And as that solar wind enters the ionosphere, the upper atmosphere, it causes the northern lights. It excites the atoms in the upper atmosphere and causes them to illuminate. So that's what the northern lights are. But the sun, the main thing about the sun is its incredible stability. It's unique among all the stars that we've studied out there in our solar system, in our Milky Way, as the most stable and has the lowest amount of flaring activity that we've observed out there. Another piece of fine tuning. So let's go on down and talk about the solar system. Solar system is made up of 8, or if you're a big Pluto person, 9 planets. And these planets are the 4 rocky planets: Mercury, Venus, Earth, and Mars. And then you've got Jupiter, Saturn, Neptune, and Uranus. And then you've got the little planetesimals that I think Pluto's been demoted into out there. But each of those is uniquely placed at the right place to maintain our circular orbit. that if we did not have a nearly circular orbit, our season would be so extreme. If we had a very elliptical orbit, our season would be so extreme that when it's farthest away from the sun, it'd be too cold, and when it's nearest the sun, it'd be too hot. So the placement of the planets, particularly Jupiter, has stabilized our orbit into almost perfectly circular. Now, Jupiter, the king of planets, is really quite remarkable. It's almost became a sun. It wasn't quite big enough to get enough heat to start its own nuclear fusion. But fortunately it didn't, because what it's been a guardian to us. Jupiter has not always been in its present place. In the past, it migrated closer to the sun, and then it migrated back out. When it migrated in, it acted like a big vacuum. It vacuumed up all the extra debris left over from the formation of the solar system, and it sucked it into itself. And then it sits back out there in a place to stabilize our orbit. But it's still acting as a cosmic vacuum cleaner, cleaning up from the big asteroids that could be life-threatening to us, and it sucks it into Jupiter. And if you remember, back in, I think it was 95 or 96, the Levy-Shoemaker comet, does anybody remember that hitting Jupiter? Well, here's what would have happened if we didn't have the internet. Let's do that. Have a good video of the Shoemaker. Sorry, technical difficulties, but the point is, the comet, this Levy-Shoemaker comet, was in a long orbit. It goes way out past the last of those planets. What's called the Oort cloud out there. And then it comes in around the sun. You see the tail, because the sun wind is blowing off the material, and it goes back out. Well, this thing got into the influences of the gravitational pull of Jupiter, and it broke it up into several smaller pieces, smaller, but they're still tens of miles across. And when they hit Jupiter, each one of the impacts of Jupiter, I'm sorry that we can't get the internet to work here. Each one of the impacts of Jupiter was the size of the Earth. So that Levy-Shoemaker comet would have been an extinction event at the hit the Earth. But fortunately, Jupiter was right there, king of the planets, great Hoover of the cosmos, sucking in all that material and protecting us. Oh, come on. Oh. Technical difficulties. Let's see if it'll work out. Any questions while the machine is thinking about things? Am I going too fast? Are you getting the gist of this? At each of the scales, it has to be just so, or else we wouldn't have this conversation here. Oh, that's too bad. I had some really good videos of the moon. Anyway, let's talk about the moon. Then we'll come back. Did you know we have a supermoon tomorrow?
Tonight's a full moon.
Well, if it's full, then it's a supermoon. That means it's the closest in its orbit to us right now. So it's going to be a few percent bigger. Well, really, the moon is really our sister planet. We are really a bi-planet system. If you compare the size of the moon to the size of the Earth, it's the largest satellite of any planet has in the solar system. If you look at the planet, the moons of Jupiter or Saturn, they may be pretty good size. Some of them are about the size of Mercury, but compared to its parent, it's extremely small. So what happened is back about a few 100,000 years after the formation of the Earth, there was another planet in our orbit called Theia. And Theia was kind of following the Earth around, proto-Earth. But under the gravitational influence of Venus, Theia kept catching up to the Earth. And then it hit about 400 kilometers a minute, an hour. No, 400 kilometers. That's either an hour or a second, I don't remember. It hit just at the right angle, just at the right speed to blow the whole two planets apart. and they swirled around each other and had a really nice simulation here. They swirled around each other, and then it congealed into the earth as we know it, and then the materials that were left over formed the moon. And it was the Apollo astronauts that brought back samples of the moon. And there's, if you've ever been to the Wings Over the Rockies, have you ever been to that? Did you see the moon rock there? They have a genuine moon rock there. It's just wonderful, just to contemplate. But that rock is worth more than any gem on the planet because it came from the moon. And it's made of the same thing in the question. So it showed that they have a common origin when they formed. So, well, one of the fortunate things about the moon hitting when it did is the Earth at that early time had a very, very thick atmosphere. If you look at the rocky planets, from Mercury, no atmosphere, too close to the sun, very hot. It looks like it's catching up. Very hot, so it blew off the atmosphere. Go to Venus. Venus has an extremely thick atmosphere. It's so thick, it's made of CO2. It's got such a strong greenhouse effect that the surface of Venus will melt lead. Well, we are larger than Venus. We're farther away. Therefore, we should have had a much thicker atmosphere, but we don't. Because Theia blew it off. Blew it off, just getting it down to just the right amount of atmosphere. And also the comets and meteors also falling in some. But just the right amount of atmosphere that our lungs would work. If the pressure were twice what it is, our lungs would work. If you go up, 20, 30,000 feet, unless you're super athletes, your lungs don't. So the pressure has to be just within fine-tuned range. And that happened because Theia blew off the upper of the atmosphere to get us down to just the right amount of pressure. The other thing the moon does is it stabilizes our tilt. With Earth tilts, we learned about this in elementary school, how seasons are made. The Earth has a 23.5 degree tilt. So when it's, if the sun were here, and it's tilting that way, we're in the northern hemisphere, we have winter, but when it's over here and we're tilting toward the sun, we have summer. That makes the seasons. Well, if the moon did not stabilize that tilt would fall off. And actually, I think it's Neptune that the tilt is pointing toward us. So if ever wobbled to that, you'd have 24-hour day light on one side and 24-hour darkness on the other side. Not really great for life. So that's another thing the moon did for us. It also slowed down the rotation. When the Earth first formed, our day was about 6 hours. Spinning that fast. With an atmosphere and Earth spinning that fast, you would have hurricanes that would have velocities near the speed of sound. So that would be good. What else has the moon done? It's given us harvest moon. It's given us romance. Another remarkable thing that I just think is just blows my mind is think about it, and you can see it kind of in here, that the moon and the sun occupy the same arc in the sky. It's about the size of your thumb. If you could look at the sun and hold it up there, it'd be about the size of your thumb, maybe a little bigger. And if you look at the full moon up there, it's about the same size of the sun. So that when they come together, you get a complete eclipse. If we didn't have that, we wouldn't have been able to see the solar corona and would not know as much about the sun as we do early as we did. So the moon is 400 times smaller in diameter than the sun, but the sun is also 400 times farther away from the moon. What a coincidence. Okay, maybe this will work. This is, and I just told you about what the things the moon does, or how the moon formed. But what would happen? I hope this works. If we didn't have it.
The moon is a giant rock that lights up our night and can even change colors. So what would we do without it? Would we all need night vision goggles? How would it affect the ocean tides, our seasons, or our sleep cycles? Or would the consequences be far more dramatic? This is what if, and here's what would happen if we suddenly had the moon. It's the closest celestial body to our planet. The moon exerts a gravitational pull that governs much of what happens here on Earth. Take the sea, for example. If you like surfing, you can thank the moon. When the moon's gravitational pull tugs on our spinning Earth, the oceans respond, giving us high tides in some parts of the world and low tides elsewhere. And while the wind gives the waves their energy, tides define their shape. The moon's gravitational attraction also keeps us at a stable 23.5-degree tilt relative to the sun, giving us 4 seasons and a livable climate. But what if that livable climate were to suddenly become unlivable? With the moon gone, its stabilizing effect on the Earth's rotation would go with it. Want the good news first? The weekend just got a whole lot closer. If the moon suddenly disappeared, a day on Earth would only be 6 to 8 hours long. Over millions of years, shifting tides and their pressure on the Earth's continents have slowed our planet's rotation, giving us 24-hour days. But without the moon's strong gravitational influence, the world would spin 3 to 4 times faster than it does now. Here comes the bad news. Rotating at that speed, we would experience winds up to 480 kilometers per hour. Birds and insects would have no chance of survival. The luckiest land-based organisms would either be deeply rooted plants or very short, very stout animals. Most of our marine life would be wiped out, since sea creatures that rely on ocean currents for survival would lose the privilege of the ocean's pull. Currents help circulate vital nutrients from the ocean floor to the surface, while dragging oxygen-rich surface water deep into the sea. We'd still have tides, but now they'd be governed by the sun. And from a distance of 93 million miles away, they'd only be 1/3 as powerful. And with the moon suddenly out of the way, the ocean would rip towards the sun, causing catastrophic waves, killing thousands and submerging coastlines. At this point, we'd have to adjust to new ocean currents, which, circulating at a slower rate, would be heating up equatorial waters while turning polar waters frigid. These extreme differences would produce a similar effect on land as well, since ocean temperatures influence their regional climates. Along with the sun, Mars and other nearby planets could also claim to share a gravitational influence over our planet, pulling Earth in different directions and causing it to tilt with increased volatility. Earth's axial plane would vary some 10 degrees, causing dramatic shifts in seasons and rendering our climate uninhabitable. Most crops would die due to drastic temperature changes. We'd experience the worst ice ages known to man, as huge glaciers from the North and South Poles would encroach upon the Earth, covering everything except perhaps a small band across the equator. So while full moons may attract werewolves, that's still better than an alternative world where the moon doesn't exist. The next time you look up at the sky, be glad it's there. Sleep soundly tonight, surf's up in the morning.
I'm glad you got to see that one. Now, we're back to our home planet Earth. Earth again is extraordinary because of the way it formed with that collision of Theia, just the right angle, just the right size, and just the right velocity to form the Earth-Moon system. It also helps seed the crust with the elements we need for advanced civilization. The metals out there that obviously your car and your electronics needs. The other amazing thing is the Earth has a magnetic field. That magnetic field is because we have a liquid iron nickel core surrounded by a solid iron nickel core, and then a mantle. And the dynamo effect caused by that liquid iron nickel core spinning, and a solid iron nickel core spinning around it is like a dynamo, and it forms a magnetic field. You can see the compass, you can see where magnetic north is. Again, if we didn't have that, we would be subject to the influences of the sun's wind, flares, and that would sputter away our atmosphere and strip it away like Mars. Mars has no magnetic field and has almost no atmosphere. Its atmosphere is about the same as if you were 100,000 feet of the Earth. So extremely fine-tuned amount of magnetic field, just enough to keep us not only shielded from the flares of the sun, but also things coming in from cosmic radiation. Another interesting phenomenon is called the faint sun hypothesis. In the distant past, the sun was about 30% less luminescent. Luminescence means hot. So it's 30% less hot in the distant past. Now, as it burns its fuel, it becomes more and more efficient and it starts to heat up. So the sun's luminosity or temperature over time has increased quite significant, 30%. Can you imagine the temperature here being 30% hotter than it is now? You think you had a bad summer. But if you look at the amount of CO2 in our atmosphere, CO2 being a greenhouse gas, and we've probably all heard about that. It has dropped in proportion such that over billions of years, the sun warming up and then the CO2 being removed from the atmosphere by photosynthesis, by weathering of rocks has been at just the right rate to keep our temperature within a very, very narrow range for billions of years in order for life to survive and for us to have this conversation tonight. So I think that that Franklin hypothesis is just mind-blowing to me. How fine tuned that is. Then, maybe we'll, in plate tectonics, I'm gonna go ahead and let this video run because I don't want to touch it. We'll talk about plate tectonics and how important it is to the earth and to us. I think the takeaway from plate tectonics is that it needs finely tuned crustal composition and thickness. As a matter of fact, if you take there's an exercise ball you sit on, the continental crust is the thickness of 11 sheets of typing paper. And the oceanic crust is the thickness, if you put it on that exercise ball, thickness of 2 sheets of typing paper. So the crust is very, very thin. And beneath it is the mantle that's heated from the bottom, from below, and causing convection. Like if you've seen when you boil milk and you watch the scum on the earth, that's a great thing to a model like tectonics. Heat milk and watch that scum happen, and watch the convection cells and pile up and push that scum around, and it wrinkles up. Great model for plate tectonics. The point is, that without plate tectonics, we would be a water world. You know, we've got erosion happening all the time. What would happen over time is all of the mountains, all the continents, we bevel down to sea level. And we would have a completely water world with a few volcanoes popping up like Hawaii here and there. We would have basically no ground. So, yeah, we would be. So, what do you think? Considering all the scales we looked at, all the fine tuning at each scale has to be just so that for us to be here, do you think that we are alone here? You know, did you watch the congressional hearings of the UFOs and the unidentified aerial phenomena, UAPs out there doing all this kind of stuff? Well, what do you think? Well, have you heard of SETI, Search for Extraterrestrial Intelligence out there? It's been going on for about 60 years now. And the biggest tool they have are these radio telescopes out there. And there was a guy named Frank Drake, who was really interested in, is there advanced life out there? So he came up with an equation. I won't go into all the terms of the equation. It's called the Drake equation. And each of these terms is a probability. A probability of having the right kind of sun, the right kind of earth, the right distance, this, that, and the other. And he tried to come up with some numbers, and you multiply all these things together. Just to give you a little refresher on probability. When you multiply a 1 chance in 6 by 1 chance in 6, like roll a dice. What's your chance of getting a 1 when you roll a dice? 1 chance in how many rolls? 1 chance in 6. So you roll 2 die, what's the chance of both of them coming up snake eyes? Is 1 chance in 6 times 1 chance in 6 equals 1 chance in 36. That's how probabilities work. So you take all these things and you multiply them together, and then you compare them to the number of known planets we think out there. And he was coming up, yeah, it looks like there's quite pretty good probability there's advanced life out there. Not so fast. As we've been studying, there have been more and more and more terms added or multiplied to the Drake equation. So this equation now has probably, I'll show you. This is just an extra out of a book. These are the number of terms of the Drake equation over time that's increased, and also what are the probabilities that there is advanced life out there? And I won't go into this. I'll just boil that down because I want you to get a chance to talk about this. But right now, well, as of this book written in 2008, there was 1 chance, 1 over 10 with 1,050 zeros.
Wow.
1 over 10 with 1,050 zeros that advanced life would arise naturally. And that was what, 15 years ago? That term is an added to. Now, is there a life out there? I don't know. Is there advanced life there? I don't know. Or UAVs? I don't know. But I'm just talking about when people say, oh yeah, there's gotta be. Well, say, well, what are you talking about? No, yes.
Life in that region is what we know to be on Earth.
You know, I'm not even going to qualify. They just say advanced life. It may not look like us, you know. I'm just saying, but life is probably carbon based. Yeah, it's probably carbon based. It's probably going to have some kind of DNA type of structure. I mean, chemistry is pretty locked down, and the temperature pressure conditions to allow that kind of chemistry is pretty narrow. I mean, I know you must like Star Trek. You like the Horta, you know, they're based on silicon, but you know, like carbon dioxide is CO2 is a gas. Silica, SiO2 is quartz. It's a mineral. It's not a gas. It's not very good for life. So my point is that there are 3.28 times 10 to the 80th elementary particles in the universe calculated. The probabilities of high-tech humans on the in the universe is 1 over 10 to 150 zeros. Far less likely than there are elementary particles in the universe. So, are we here by mere chance? Or are we here by purpose? Yes.
On our trip to Arizona a few years ago, We passed through this place in New Mexico where they have all these satellite dishes
Mhm.
supposedly listening for outer space to talk and stuff. The government's paying for that?
Well, those are radio telescopes and used for astronomical investigation. SETI will rent time on those things. You ever seen, Contact, the movie out there, they'll show them out there. So yeah, they don't have them set on dishes, it's too expensive, but they'll rent time on them and they'll look at them places. And, you know, one of the reasons that we fund all these space probes out there, every one of them has in there, looking for life, looking for life, looking for life. That's kind of the key to getting your grant funded, looking for life, and that's okay. In Mars, we've been looking for life since 1974. I mean, there's water there, there's been water there. That's one thing you need, but that's just one of them, just multitude of things you need. And so the takeaway here is the fine tuning goes from the largest scales down to the smallest scales. And if they weren't such, we would not be here today. So. Yes.
How does the universe know?
Well, we think it's about 3.8 billion, and the Earth is about a little over about 4.53 billion. Yes. What?
About 6
That's a whole different conversation. If you're talking about old Earth and young Earth, that, to me, that's not a theological conversation, that's a scientific conversation. It has nothing to do with something. Yes.
That was essentially my, well, it's maybe this is a whole other conversation
It
as
is.
well, but, as far as apologetics is concerned, in those who are atheists or in scientific realm, I would assume that an old Earth, I don't know what to call it, understanding is more bridge, is more of a bridge than a young Earth understanding for those who are in the sciences.
Yeah, I know you guys want to break up, but this is a whole different conversation. And that's why I'm in this organization called Roots to Lead. And by the way, we meet every third Saturday of the month at Cherry Hills Presbyterian Church, 9 o'clock in the morning. And you're all invited.
Cherry Creek.
Cherry Creek Presbyterian on Bellevue, on East Bellevue. So that's what this ministry is all about, is reconciling the book of nature, the general revelation, with the book of scripture, the special revelation. Is trying to understand both of them in the context in which they're presented. And it's a lifelong study. It's fascinating.
But there are more scientific, people of science that believe in God than you realize.
I will say that there's a larger percentage of astronomers that believe in God than biologists. Yes.
You know, that,
Mhm.
but when I talk to people about time. I have to remember that, right, there are more Christians that are believers than not. And if you want to go near the evolution area, with the human evolution, you know, if you're a Christian, it's not hard to believe that so it's really,
I would say it's been a stumbling block for a lot of people. You know, we should, really live beyond the world that's next to nothing to do with yourself. It's just. Well, you know, like creating with your parents' age. Well, all I can say is about them.
Thank you, Fred. This is excellent.
Yes.
Shall we go to our discussion time and, everyone feel free to spend some more time with Fred tonight if you're able to stay longer. but let's go back and discuss it, Craig.